Hi there, welcome back. Last session we talked about lever. Today we're gonna continue Unit 1, Lesson 2, Law of Lever. We studied before that lever is a rigid bar, straight or curved, rotate around fixed point, and affected by two forces, effort force and resistance force. Today we're gonna talk about law of lever. As you can see, we're gonna illustrate first arm and resistance arm and predict possibility of first class lever to save or don't save effort, and infer the levers that save effort by applying the law. Are you ready to start? I hope so. As you can see from the first picture, it's scissor. If I ask you about the type of lever, so I have to determine the position for the structure of lever. As you can see, here is fulcrum. So fulcrum at the middle, so it will be first class lever. That's right. The second example, nutcracker. As you can see, here is the resistance at the middle, so it will be second class lever. Here's third picture. I hold it from the middle, so here is effort force, so it will be third class lever. It's easy. That's right. How does lever work? To answer this question, you have to know that when you exert an effort on one arm of a part of lever, load occurs on the other part, right? So if here I exert an effort, so the load occurs in the other part, which is resistance. Okay, so I said I can call resistance load. It's the load for the body. So the load generates a resistance force. Here, load generates resistance. And the length for the lever makes work easier. So as you can see, if the distance here, if this distance increases, the needed effort force decreases. So according to the type of lever, sometimes the effort force less than resistance force, sometimes more than, sometimes equal. So we're gonna study in details each case and what happened to the lever, if it save effort or not. As you can see, here's fulcrum and here's effort, here's load or resistance. The distance here from fulcrum to effort, it's called effort arm, and here it's a distance between fulcrum and load or resistance, it's called resistance arm. So I can say that force arm, it's a distance between effort force and fulcrum, and as well resistance arm, it's a distance between resistance force and fulcrum. Here is resistance arm and here is force arm. So what do you think if force arm equal resistance arm? What do you think? For example, seesaw. It's an example for force arm equal resistance arm, right? What do you think about this type of lever? In this case, the lever conserve or save any effort? That's right, no. This kind of lever doesn't save any effort. That's right. What do you think about when force arm is shorter than resistance arm? Force arm, which means this part. It's a distance from here. It's shorter than resistance arm. What do you think about it? This lever doesn't save any effort. That's logic because If the force arm shorter than resistance arm, so here the resistance force more than force arm, so it doesn't conserve any effort or doesn't save any effort. But what will happen if the force arm longer than resistance arm? It's the only case the lever save effort. Why? When the force arm longer than resistance arm, as here in this picture, imagine if this arm longer than this arm. So I will put a small force or a small effort, and it will be less than the resistance force, so it save effort. So when I ask you, force arm is longer than resistance arm, this type of lever save effort or no? Yes, it save effort for sure. So if I want to find the if this type of lever conserve effort or not, what can I do? As you can see here, we have different cases. In case first class lever, we said that in the first class lever, the fulcrum at the middle, and here is force and here is resistance. Okay, first case, if force arm equal resistance arm, like picture 1. So the lever doesn't conserve effort and has no mechanical benefit, like seesaw. Second picture, as you can see, resistance arm here more than force arm. So this lever doesn't conserve effort also. What do you think about if force arm more than resistance arm? Force arm more than resistance arm, so force is smaller than resistance. When the force arm more than resistance arm, this means that force is smaller than resistance. If I apply small force, so this type of lever will conserve effort. Got it? Yes. So lever conserve effort and has mechanical benefit. Okay. Second case, or in second class lever. If the force arm more than resistance arm, this means force is smaller than resistance, right? So these levers always save effort. When the force is smaller than resistance, so I apply small force, and the resistance is also force is smaller than resistance. Force is smaller, so it conserve effort. So it save effort. Got it? When the force arm more than resistance arm or longer than, it save effort. When force is smaller than resistance, it save effort. That's right. So in case third class lever, as you can see here, here is fulcrum, here is resistance, here is force. What do you think about it? If the force is longer than resistance, force longer than resistance, as you can see, so it doesn't conserve any effort because the force is larger than resistance. So I apply larger force. So how it conserve any effort? I apply larger force. Got it? So force arm here is shorter than resistance arm. As you can see from the picture, it's so short. Here's force arm. Here is resistance arm. Look how it's so long. So force is more than resistance, so it doesn't conserve any effort. So what is the law? If you want to calculate it, you have to measure all of these. Effort force times its arm, resistance force times its arm. Maybe you ask about the measuring unit. What do you think about the measuring unit of effort force or resistance force? What do you think? Yes, that's right. It's a force, so I measure it by Newton. That's right. What about its arm? It's a distance, right? So I measure it by meter or centimeters. That's right. When I ask you, what do you think about the factors that determine the values of effort force and resistance force? Super, that's right. It will be force arm and resistance arm. Okay, let's practice. Here's the question from booklet. Number 1, the values of effort and resistance force and fulcrum is arm of force or arm of resistance or position and of fulcrum or A and B. Yes, as they said, the value of effort and resistance is determined by the arms for force and resistance. So it will be D. Next question. When the arm of force is space, the arm of resistance, the effort force equals the resistance force. So logic, it's equal C. When the arm of force space, the arm of resistance, the lever conserve effort. When the lever conserve effort, so the arm of force longer than the arm of resistance. Got it? Yes, sure. Okay, number 4, the effort force and resistance force. How can I measure forces? With Newton, that's right, it's D. Number 5, the type of levers which sometimes has a mechanical benefit is dam. What do you think? The type of lever that sometimes has mechanical benefit. What do you think? Which is always save effort. Second class lever, that's right. Next question. Which of the following levers save effort? What do you think? Nutcracker or sweet holder or scissors or fishing tool? Logic, nutcracker. By using small force, it can break the nut, so it saves effort. Super. Okay. That's all for today. Thank you for listening.